Okay, so today we are going to be exploring chapter 16, which is The More Things Change. So this is basically about different translations that includes rotations, reflections, and other types of translations. So yeah, I like this chapter because I think it's the simpler side, but it's also a fun chapter. Okay, so a translation is a geometric transformation that moves every point of a figure or space by the same distance in a given direction. So we say that A is the image of A under the translation, and we can also claim that the translation maps A to A. So we can translate any figure, a segment, a line, a triangle, a quadrilateral, etc. And remember that the result will be congruent to our original figure. So in this case, we see that point A and point B have been translated to their new set of points. But even if they are moved, they're still going to be the same point. And as the example stated earlier, you can translate, you don't have to just be, you can also translate different shapes. So you can translate, I would say, basically everything. I can't think of a thing that you can't translate, as long as, it's like a segment, a line, a dot, or a shape. All right. So a fixed point of a translation is a point that does not move or change its position. So if we go back, we can use this example. Let's say that point A was a fixed point, so that means that it wouldn't move at all. So the translated image would actually still be at point A. So the identity transformation is a transformation that maps every point to itself. And that's basically what we were talking about when we were saying, oh, point A doesn't move. That's a fixed point, therefore it stays at point A. And can a translation that isn't the identity also have a fixed point? And the answer is no. Every point is moved the same distance in the same direction in a translation. If there's a fixed point, then that means that none of the other points will move. So the only translation that has a fixed point is the identity. So if you were to translate a point, what this is saying is that if one of the points are, if they don't move, then that means that the rest of the points don't move. But then at the same time, in a translation, in order for a whole figure to move, all of the points have to move. And the shape that results from the translation has to be the exact same shape of the original shape. So next we have 16.2, which is rotations. And a rotation is a transformation that turns a figure about a fixed point called the center of rotation. So for example, if you want to look at this image here, the image of point A under the rotation of angle theta in the counterclockwise direction about point A is going to be this new point A, so that the original OA is going to be equal to OA, and angle AOA is going to be equal to theta. So there are two existing points that satisfy this definition of the new point A. As a result, we must specify which direction we are rotating in, clockwise or counterclockwise. So another way you could have translated this point was you could have moved it in the complete opposite direction. So yeah, just make sure when you're transforming, or if you're rotating something, you just specify which direction you're going in. And the image of any rotated figure is congruent to the original figure. So point A is going to be congruent to the new point A, and the new point A is going to be congruent to the old point A. So they have to be the exact same. So I'll leave us up here for a few seconds and then we can move on to the next slide. Okay. So, here's problem 16.3. O is the center of equilateral triangle XYZ. So the first question is, through what angles between 0 and 360 degrees can we turn Y around Z so that the result is point X? And the second question is, through what angles between 0 through 360 degrees can we turn X about O so that the result is point Y?
What is that sound?
It's the it's my dryer.
Your dryer has a bell?
Yeah,
I mean,
it
bell,
makes
it
a
has
noise.
a sound.
Yeah.
I saw your kid. I saw you had a kid that was playing.
No. Okay, I'll go ahead and go over the answers for this one. So we know because this is an equilateral triangle, the sides are going to be equal to each other. So YZ is going to be equal to XZ, and angle YZX is going to be 60 degrees. So a 60-degree rotation clockwise around Z takes Y to X. A 300-degree rotation the opposite direction will also work. So for the second one, O is the center of triangle XYZ, so XO and YO, XO, YO bisect angle XC, XCY and angle ZYX. So angle YXO is equal to angle OYX, and that's going to be 30 degrees, which means that angle XOY would be equal to 180 minus angle YXO minus angle OYX, and that's going to be 180 minus 60, so that's 120. And because OX is equal to OY and angle XOY is equal to 120, if we rotate X 120 degrees counterclockwise around O, it's going to be mapped to the point Y. And we can also rotate X 240 degrees clockwise about O to get to Y. So as you can see, you can rotate, I think it's pretty straightforward, but you can rotate the shape in 2 different directions and you'll still get the same result. Okay, I will go ahead and move on to the next section, which is 16.3, and we are going to be learning about reflections. So a reflection is a transformation that takes a shape called the pre-image and flips it across a line called the line of reflection or line of symmetry to create a new shape called the image. So we can reflect points, lines, shapes, etc. In this example, you can see that line K is the line of reflection or the line of symmetry, and the original shape was ABC, the pre-image, but then we flipped it over, line K, to get the new image, which is this other triangle that's on the right side of line K.
So it's basically a geometric, a 2D geometric mirror.
Yes, it's, yeah, you can think of it as a mirror. You're flipping, yeah, or you can. I also would like, when I was learning about this, I imagined that I was maybe flipping a page of a book or something, even though that's, I mean, it doesn't directly correlate to, you know, I guess, I don't know, or it was just another way of thinking about it, because let's say that this triangle over here was like, it was all the way over here, then there will be a certain gap between the new triangle that results over on the right side of line K. But yeah, so you can think of it as if you're looking at yourself in the mirror, or you're flipping a shape across a mirror. Okay, so next we have problem 16.6. What are the fixed points of a reflection of a line such as line M? Hold on. Here, I should say on a line, sorry, or of. So this is just, think of a line, and then imagine that you're reflecting it across. You can reflect it, for example, I think an easy way to think of this is reflecting it across the y-axis. You could also reflect it across the x-axis, of course, but I would say that's the easiest way to imagine this problem.
I don't see any shape.
Yeah, so just like imagine. Like, so what are the fixed points of a reflection on a line, such as line M? I guess we can use, you can think of, I guess the past example doesn't give us a good image. Yeah, this, so I guess I could have supplied an image for this one, but you're originally supposed to think of it like without an image, a reference image. So yeah, just try to imagine that you have a line, and then you're reflecting that line over an axis of symmetry, or the x or y axis. Okay, I'll go ahead and go over this problem. So in this problem, I just said that I was reflecting. I shouldn't have said line M. I should have said like a different line. But to give you different examples, I said that like you could reflect a line over like the x-axis or y-axis, but in this case, you would have been you would be reflecting it over a line. So that x-axis or y-axis could have been line M. And then I said that you were flipping a line, but you could also flip a shape or a point. You could flip anything across an axis. So just to go back to the reference, this image, you could see that, okay, so we're flipping this image across line K. You can imagine that this line K is actually line M. But if you notice, all the lines, they map back to the original image itself. So that was just what the goal of the question was, to make sure that you could see that the original point or shape or line will always map back to itself, even if it's been flipped across a line. Okay. And yeah, so every point on M maps to itself because M is the quote unquote fold. and any point that is on one side of M is mapped to a point on the other side. In other words, a point not on M can't be mapped to itself. So, okay, let's see. When I was typing up this problem, I was trying to see if they would give me like an image that went along with it, but they didn't. So, okay, imagine, let's say that there's a line M, and let's say that there is a point on the left side, point A. If we flip that over, that's going to be the new point, or so the original point would be pre-image point A, but then the new one would be the image of point A. But then if you had a point on line M itself, you can't exactly, reflect that over the line because it's actually on the line itself. So it's just going to stay there. And yeah, I think that's pretty straightforward. Okay. Next, we have problem 16.7. So given two different points, X and Y, describe all lines M so that the image of X upon reflection over M ends up being point Y. So this, imagine that this is, I know it says given two different points, X and Y. I just wanted to supply an image so that it would be like a little bit maybe easier to figure out what the problem is asking for. This image doesn't directly correlate to this problem, but it has the same concepts. So imagine that you have, two different points, and so then what you would want to do is you would flip those 2 points. But then we just have, in this case, we just have one point, which is point A, but we're still flipping it over. And yeah, so you want to describe all lines M so that the image of X upon reflection over M ends up being point Y. So I think honestly this image actually kind of answers the question. If you imagine that this is point X and this is point Y. Okay, I'm going to just go over it now because I think this image kind of gave away the answer to the problem. But the image of a point A that reflects over a line, not Lin, is the point, or is the image A, so that the line AA is the perpendicular bisector. Because the image of X in our problem is Y, the line over which we are reflecting has to be the perpendicular bisector of XY. So imagine that this was X and this is Y. That means that M would be the perpendicular bisector of line XY. Okay. Moving on to problem 16.8. A regular hexagon has how many different lines of symmetry?
Doesn't it say here?
Yes, so you want to count it up. But you want to be a little bit more careful.
Can I say something?
Yes.
So for any regular n-gon, n is greater than or equal to 3 and is a natural number.
Mm-hmm.
If n is an odd number, the number of lines of symmetry is literally just n. And if n is even, then the lines of symmetry is 2n. For example, this is 6-gon, and because 6 is even, so the number of lines of symmetry is just 2 times 6, which is... You know what I mean.
Did anybody hear a pot or something?
A pot?
Something
A
just
pot?
Something just went bang.
That might have been, I don't know.
Yeah, I heard a pot too.
I thought it was a pot, but something went.
I thought it was a pot too.
Well, you're not the only one who's cooking tonight.
Don't cook.
So one
I'm saying your parents or whoever cooks for you.
one way that you could have figured this out is, yeah, you could have just counted the lines. So it'd been 1, 2, 3, 4, 5, 6. So that would have been 6 different lines of symmetry. But another way you could have, I guess, thought of this was that they're, so as Alvin said previously, that there are 12. So you could have counted like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Depending on what the question asked for exactly, your answer could be 6 or 12. In this case, when it said a regular hexagon is how many different lines of symmetry, so if you wanted to, you could split. In this case, they're asking you to completely split the hexagon in half. So then in order to do that, you would have drawn 6 full lines. So for this question, you could say that there are 6 different lines of symmetry. Okay, next we have dilation. So dilation is a transformation that produces an image that is the same shape as the original, but is a different size. A dilation that creates a larger image is called an enlargement. So for example, we have an example of a dilation here on the right. So we have the original image of triangle ABC, the pre-image, but then we dilate triangle ABC so that it becomes image ABC, ABC, yes, triangle image ABC. And this one would be an enlargement because the pre-image expands and the image is larger than the pre-image. So here's a little bit more information about dilations. Point O is the center of dilation. The image of point A is the point A on ray OA, so that's OA divided by OA equals 2. You can see, so that would mean that A would be the midpoint of, you could say, segment OA. And same thing for the line below. Image of point, or this ray below. Image of point B is the point B on ray OB, so that's OB divided by OB is equal to 2. I'll leave this up here for a few more seconds and then we can go ahead and go to the next problem. Or more information about dilations. Okay. So generally speaking, the image of a point P that is dilated with scale factor K, and let's see if I have an image for that because that's a lot of words. Okay, or I'll just describe it. Sorry. So generally speaking, the image of a point P that is dilated with the scale factor K and center O is the point P on ray OP, so that OP is equal to KOP. So in our previous example, the scale factor is 2. So what this is saying is that this is just explaining how there is a ratio when you compare the original image to the dilated image. So in this case, this became, so here's point A, and this is OA. The new image segment OA, that is twice the original line segment OA, so then that means that the scale factor is going to be 2. At the same time, though, the scale factor can be negative. On the right, the scale factor is -2. The image of point X upon dilation about point O is the point X on the ray that starts at O but goes in the opposite direction from X, so that OX divided by OX is equal to 2. So you can see that this is moving from the right to left. So as a result, that would become -2, because, you know, if you go to the right, like on a number line, if you go to the right, that's positive, but then if you go to the left, that's negative. So that's why. And point X is the point such that OX divided by OX is equal to 2, and O is on XX. Okay, I will go ahead and leave this up here for a few seconds and then we can move on to the next slide.
Where's Alvin?
I don't know, did he leave or?
He has disappeared.
Oh.
Oh, nope, he has reappeared.
Okay.
Hi.
Okay. So if the scale factor of a dilation is greater than 1, then the dilation of a figure quote unquote stretches the figure and the resulting image is bigger than the original figure. If the scale factor is positive but less than 1, so then that's 0. It would be greater than 0 but then less than 1. The dilation is a shrinking of the original figure and the resulting image is smaller than the original figure. And if the scale factor is equal to 1, then the figure remains unchanged. So on the left, we can see an example of a dilation where the scale factor is greater than 1. So then the image is greater than the pre-image. But then for on the right, we can see that the scale factor is less than 1. So then the pre-image is the pre-image is greater than the image.
I have a question. How do we tell the which is the original shape?
Oh, okay. The original shape is not going to have this. You see the apostrophe sign right here? So this would be the original shape because it doesn't have the apostrophe sign, but then if there's an apostrophe sign next to the point, then that is the new shape that results from the dilation. So yeah. Okay, next we have problem 16.12. So square ABCD is the image of a dilation of square ABCD about point A with a scale factor of 3. And suppose AB is equal to 2. Find AA, AB, BB, BC, and CD. So this is AB, CD, and A is equal to the image of point A is equal to the pre-image of point A. So yeah, they're going to be equal to each other. Give you guys some time to figure this out.
Isn't A? I don't think A apostrophe isn't even a line.
Yeah, so that's going to, what do you think that's going to equal?
Zero.
Yeah.
Zero.
Yeah, it would equal 0. Okay, I'll just post the answers. So yeah, the image of A upon dilation about A results in just A itself. So AA is going to be equal to 0. And B is the image of B upon a dilation about A with a scale factor of 3. So AB is divided by AB is going to be equal to 3. So that means that B is 3 times as far from A as B is. And because AB is equal to 2, you're just going to do, you could do 2 times 3. So then that'll be equal to 6. So AB would be equal to 6. Points A, B, and B are collinear since B is the image of B upon the dilation of A. So AB plus BB is going to be equal to AB, and then we can then figure out that BB is equal to AB, which is 6 minus AB, which is 2, so that's going to be 4. Okay. So next we want BC and CD, and I'll make sure to go back to the first part of the answer for review, but back to finding BC and CD. So we have lots of right angles, so we can search for right triangles. Previously, we found that AB is equal to 6, so square ABCD has side length that is equal to 6. And we also found that BB is equal to 4, so then that means that the right triangle BBC is going to give us the following, where BC is equal to the square root of BB squared plus BC squared. Just notice that I know I'm just saying like, BB divided by BB is equal to whatever. Just make sure that you pay attention to when there's an apostrophe and when there's not, so then you can figure out the different line segments that I'm talking about. Okay, back to the problem. So we used the Pythagorean theorem and got this formula, and then we can plug in numbers. So we get the square root of 16 plus 36 is equal to 2 times square root of 13. So we can use the same method that we used to find BB in the first part to find that DD is equal to 4. So the right triangle CDD then gives us the following. So CD is going to be equal to the square root of CD squared plus DD squared, and that's going to be the square root of 4 plus 16, which is 2 square root 5. Okay, so I'll leave this up here for a few seconds, and then I think the first part of the problem was pretty straightforward. I'll still go back to it for review, but I don't think we need to spend too much time on it because I think this part of the problem was a little bit more complex than the first part.
Can we take a break right now because it's practically almost 7:45.
Want to take a break now?
No, 7 minutes later.
Yeah,
Okay.
7 more minutes. We can
Up to Zach's games.
Okay, I'll go back to these solutions for a few seconds. Okay. So next we have important information. A figure and its image that is dilated are similar. The ratio of corresponding sides of the figure and its image is equal to the scale factor of the dilation. So that's one thing that I mentioned previously, I think, and I feel like you guys would have also noticed that the ratio between the original figure and the dilated figure, and at the same time, because in this case, the dilated figures aren't congruent to each other because the side lengths are going to be, for example, when we're talking about shapes, the side lengths would have different measurements, but then we still need to take into consideration that these two shapes are going to be similar to each other. So triangle OAB is going to be similar to triangle OAB, the bigger triangle, or the dilated triangle. Okay, I'll leave this up here for a few seconds, then we can go to the next section.
Can the dilation factor be 1?
Yes, remember, so if we go back here, if the scale factor is equal to 1, then the figure remains unchanged. So yes, you can have a time when the dilated image or the scale factor is equal to 1, but then that means that the image is just going to
Also,
be...
another thing, two
Yes.
shapes, if they're dilated, the scale factor is equal to the square root of their areas. Like, the course, like if because if I say like ABC and A apostrophe B apostrophe C apostrophe, then so if you like, then the scale factor is the square root of ABC the square root of A apostrophe V apostrophe C apostrophe divided by ABC, like the areas.
Oh, okay.
Because the height is the height of the scale factor, and the base is scale factor, and then you multiply two scale factor and get the scale factor square. So you have to square root it to get the scale factor. I don't think I said clearly, so whatever.
Okay. I did not know that information, so you learn something every day, but thank you for giving us that piece of information. Okay, next we have 16.5, which is our last section, and we're going to be quote unquote changing the question.
At first, before you said the quote unquote, I was like, wait, you can change the question?
No.
If it did, that would have been really fun. That would have been really funny.
All right. So we have problem 16.14. So the largest square side length pictured on the right is 10 inches. The midpoints of the largest square sides are connected to form a smaller square. Opposite vertices and midpoints of the smaller square's opposite sides are then connected. What is the number of square inches in the area of the shaded region? So this image was supposed to be part of the solution, but I just left it up there just for like a hint in case you guys wanted to have one.
Can it just be 2.5? Wait, no, sorry, not 2.5. Wait, is it 10 inches squared or just 10 inches?
Just 10 inches. If it was 10 inches, remember we deal with like inches squared when it comes to area. Okay, I'll go ahead and go over the problem.
Can I say how I did it?
Yes.
So, first of all, the small square's area is 1/2. So like the small square's area is 1/2 of the large square's area. Because it's the midpoints, and if you like, so you just have the area, and then the shaded region is half the area of the small square. So basically, the shaded region is 1/4 the area of the big square, and the big square's area is 100. So the shaded area is 100 divided by 4, which is 20.
That's actually a really efficient way to think of how to get to the solution. So good job, Alvin. So that was actually also, I think, a simpler way to think about it too, and a faster way. But yeah, so the area of the small square is going to be 1/2 of the bigger square, and then the area of the shaded region is going to be 1/2 of these smaller squares, so then that's going to be 1/4 of the bigger square. So yeah, you would get 25 because we know that the side length is 10. So you would have done 10 times 10, and then 125 divided by 4 is 10. So good job, Alvin. Okay, it's 7:46, so I would say go ahead and take our break now. And yeah, we will be back in 5
Alvin,
minutes.
Discord.
Yep.
We have some business to. We have some business we attend to.
Totally. Did you import the sprites yet?
Nope, I told you I didn't have enough time to look on Discord.
Sure, let's start. So can you start the meeting?
Okay.
What do you mean by PVZ supporter? Whatever. Hi. Wait a sec. I'll mute.
Yep,
Okay.
you unmuted.
Tesla mute. Mute. Tesla mute in your
Okay, so it's 7:51, so we can go ahead and start where we left off. Okay, so next we have problem 16.5. So a circle is inscribed in a large square and circumscribed around a smaller square. The largest square's area is equal to 8 square meters. Find the smaller square's area in square meters. So I'll give you guys some time to figure out this problem. Okay, I'll go ahead and go over the problem. So because our large square has an area of 8 square meters, each side length must be equal to the square root of 8, which is going to be 2 square root of 2. Since the circle is tangent to all 4 sides of the large square, the circle's diameter equals the large square's side length. Because if you were to draw the diameter here, that would be equal to DC or AB. But the small square diagonal is also a diameter of the circle. So the diagonal of the small square is going to be equal to 2 times, should be 2 times the square root of, I believe, 2, yeah, inside of that parentheses, sorry. So its sides are each 2 square root times 2 divided by square root 2, and that's going to be equal to 2, and its area is going to be 2 squared, which is 4. And that'd be 2 inside. Okay. So I'll leave this up here for a few more seconds, and then we can go ahead and move on to the next problem. Okay, and so we're going to move on to the last problem of chapter 16, which is this problem. So in the figure, ABCD is a square that has a side length 1, and M and N are the midpoints of AB and CD. Find the area of the shaded region. Okay, I'll go ahead and go over the solutions for this problem. So MBYX is a trapezoid, but how are we going to figure out the height or the bases? It's also not clear how we could chop MBYX into pieces that we can handle, but it looks like MBYX is congruent to NDXY. And to figure out if they truly are congruent, we can just rotate MBXY. And if we were to rotate it around Y, I think, oh no, actually, let's see.
I have a solution.
Yes.
So first of all, because MBYX is congruent to XYDN, so the area of MBYX is 1/2 of the area of MBND. MBND, the area of that is 1/2 the area of the square.
Mm-hmm.
Like if you like connect MN, then it like because the height is the same as the square and its base is 1/2 of the square side length. So the area of MBND is 1/2 of the area of ABCD. ABCD's area is 1 square, which is 1. So the area of MBND is 1/2. So the area of MBYX is 1/4.
Yeah. So that's what Alvin basically mapped out what the solution says down here. But yeah, so you would have you could rotate actually triangle ABC 180 degrees around the center of the square so that you could figure out that the trapezoids were parallel to each other. Or the quadrilaterals, I guess, because we exactly don't know if these are trapezoids, but they look like trapezoids. So the area, as Alvin was talking about, of MBYX is the area of MBND. MBND is a parallelogram with base ND, which is 1/2, and height BC is 1, so its area is 1/2. So the shaded region has area 1/2 divided by 2, which is 1/4. So yeah, that's how you would have gotten the answer. Good job, Alvin. Okay, I'll leave this up here for a few more seconds. And there were actually some problems that we didn't finish from the last section of chapter 15. So we can go ahead and go over those problems. I think there's like maybe 4 or 5, but we can just go over, if we can't finish all of them, because I think I want to have about 17 minutes for the Kahoot. We can just go ahead and go over the rest of the problems in upcoming classes, because I think the next sections are on the a bit of a shorter side too. Okay. Here.
You're a little bit lagging.
Laggy?
You're lagging.
Is my audio lagging?
No, part of it was the share screen, but then you for some time you stopped your audio stopped. I couldn't hear you talk. I couldn't hear your mouth moving.
Oh. Well, what I was just saying is that we're going to go over the last few problems of chapter 15 because we didn't go over those problems. And then we can, I don't think we're going to be able to go through all of them because there's like, actually maybe, but I'm not sure. But I want to have time for the Kahoot at the end. So yeah, just how far we get. If we don't cover all of the problems, then that's fine. We'll just cover the rest in an upcoming lesson because the next chapters are on the shorter side. Okay, so for this problem, 15.14, the areas of 3 faces of a rectangular prism are 24, 32, and 36, and you want to find the volume.
Okay, so first of all, can I say something?
Yes.
So, 36 must be a square because 36 must be a square because we can just say that 36 is a square and the other two sides are rectangles. Could we?
Wait a sec. Isn't I don't think that makes sense because the square looks like the smallest side while 36 is the largest number.
Yeah, so you just because 36, you can square root 36, you get 6. That doesn't necessarily mean that that's going to be the squares, the area of the square.
Yeah.
Because you can also square root 24 or 32. So that's a good way to think about it, but you have to also consider the other possibilities. Okay, I'll go ahead and go over the problem.
Can I say how I would do it?
Yes.
So the three faces of a rectangular plane are 24, 32, and 36. If we say they're LWH, because I don't actually, I would just call them XYZ. I don't want them to have like, okay, so if we say XY is 24, XZ is 32, YZ is 36, then we'll get like three equations. XY equals 24, XZ equals 32, and YZ equals 36. We multiply the three equations together, and we get XYZ squared. X squared times Y squared times Z squared equals 24 times 32 times 36. You square root that and you get XYZ is and the answer. And apparently, let me take a look. Oh, so you got 96 square root 3. Okay.
Yeah. Yep. So that was the solution basically. Yeah, so you would multiply, you would come up with the following equation: x squared times y squared times z squared is equal to 24 times 32 times 36. And you would have taken the square root of 24 times 32 times 36 to get 96 times square root of 3. And yeah, that's the solution. Good job, Alvin. Okay. Next, we have problem 15.5, and we want to find angle WYT in cube STUVWXYZ. So if you look here, WYT, that's the angle that you want to find. And then you can, if you want to look at either image, it shows the cube.
So, so we can first break this problem up into two sections. So first of all, WY, not the problem, but the angle WYT. We can say that WY is 40, the angle WY is 45 degrees and YT is 45 degrees.
Mm-hmm. Okay, I'll go ahead and go over the problem. So we don't know how to handle angles in 3D exactly. I mean, you could, technically we could, but I guess, or this is a little bit just harder. So we have to consider the 2D figure that includes angle WYT. So we want to consider the cross section that contains angle WYT. So we would form the cross section by cutting through the cube's vertices W, Y, and T. And the cross section, therefore, is going to be a triangle, as you can see. So because each of triangle WYT's sides is diagonal of cubes. Oh wait, I didn't have the solution. Sorry. So because each of triangle WYT's sides is a diagonal of the cube's face, the sides of triangle WYT are all equal. So triangle WYT is equilateral in each of its angles, including angle WYT is going to be 60 degrees.
So can I sort of
Yes.
summarize what you said?
Yes.
So because the cross section of this the cross section of these the cross section formed by cutting through the cube's vertices that are in the problem W, Y, and T, we can conclude that the cross section is an equilateral triangle. So all the angles are equal. So each one, which includes angle WYT, is 60 degrees.
Yes. Yep. Okay. Next, we have this problem. So Michael the ant is at point A of cube A, B, C, D, E, F, G, H with edge length 1. He wants to walk along the cube's surface to point G, where G is the cube's vertex, such that AG is the cube's space diagonal. What is the length of the shortest path that Michael can take?
Yeah, it gives the answer. The picture gives the answer. That is the answer.
2 inches. Wait, no, sorry, not 2
But
inches.
actually, it's not an answer.
I know. I know. I took when I saw the problem more carefully, I took it back.
Okay. Let's see. I'll give you guys a few more seconds, and then we can go ahead
Can
and
I
go.
explain it after a few more seconds?
Do you want to? Sure, you can explain it if you want to. Do you have a
So
solution?
now?
Yeah, you can. Yeah.
Yeah. So I've done this question before. The way you do it is, first of all, you put A, B, E, F, E, and B, C, G, F on the same plane, and then you connect A, G, and then you put B, C, G, F back to its original place, and yeah, you did that too.
Yeah, right there. You can keep going though. You can keep explaining. Or no.
And then it would just be like AX, X is the midpoint. So A, and then it goes through X. X is the midpoint of BF, and then it goes from X to G.
Yeah. So the shortest path, that would be A to G, can take, so we would figure out this is square root 5 because AB is equal to BC, which is equal to CG. That's equal to 1. So you would have done the Pythagorean theorem. So you gotten the square root of CG squared plus AC squared, and that's going to be square root 5. So the shortest path Adam can take is, or it should say Michael, not Adam. I think Adam might be another character that we deal with. Can take is square root 5. So since AB is equal to FG and AC, and that's parallel to EG, we can use the congruent triangles ABX and GFX to prove that BX is equal to FX. This means that Michael's shortest path does go through the midpoint of one of the cube's edges.
But that doesn't solve the problem. Oh.
Oh.
There's no answer.
So yeah, I think this is just additional information, but the shortest path that Adam could take was square root 5.
Okay.
Yeah, we got it up here.
Also, why are there 2 ants?
It's supposed to, I meant to, I don't know where I got it.
Did Adam just come along and then say, hey, I want to join this math problem?
Should be Michael. Michael is the star of the show. Okay.
Phew, Adam was trying to take his place.
That would have not been good. Okay. So Michael the ant is now on point A. He wants to walk along the cylinder's curved surface to point B, where BC is the cylinder's height and C is on the top base such that AC is the diameter. Knowing that the cylinder has a height 4 and radius 3, what is the shortest path length that Michael can take?
I have a question. Wouldn't going diagonal be a little bit faster?
Yes.
Okay, one thing. Can ants walk through walls?
No, unless they eat through the metal. And I'm actually not. No, this is not a joke. They can actually eat through metal.
I know, but I don't think that would taste good.
That's why they have a thing called mouths. They have another mouth. They have another mouth so they can spit things out.
Let's see. Okay, there we go.
So
Okay.
theoretically it can, but just don't think about this in this problem.
Okay. So it was actually technically correct because you would form a diagonal shape. I mean, you wouldn't go directly through the cylinder, but you would actually unroll the cylinder, so then you could get a diagonal. So BC is going to be the cylinder's height, and that's going to be equal to 4. But AC is not the original cylinder's diameter, but rather the distance from point A to point C along the base's circumference. So AC is going to be equal to half the circumference of the cylinder's base, which is 3 pi. So then from right triangle ABC, we can find the following. AB is going to be equal to the square root of AC squared plus BC squared, which is the square root of 16 plus 9 pi squared. So that's going to be our final answer. Okay.
17 minutes for Kahoot, just as you said.
Yep.
Gatling P2000 shall destroy you all again. Okay, and also, I have a question. Raise your hand or just speak out loud. Who was Doomshroom last time?
Doomshroom.
Who was Doomshroom? And Izzy, your video.
I do not see the code.
Yep, I do not see the coach either.
I see Kahoot, geometry review, player versus player, one column 1, devices classic, team versus team.
1-to-1. Do you not know ratios? It's 1-to-1. What's 1-to-1 ratio?
Okay, the teacher left.
The teacher left because of internet problems.
I wish I were the host.
Wait, she got what?
She got kicked.
Oh, Izzy's back now. Hello.
Sorry, I lost connection. My Wi-Fi is really
Now we have
unstable.
only 15 minutes of Kahoots.
Wow.
We can go a little bit over time, so don't worry. We'll finish the Kahoot.
Okay, let's do this.
Let's do this.
Let me share my screen. Oh, wait. Cloud Classroom, if you can enable me to share my screen. Let's see. Okay, wait. I'll give you the code. Cause let's
In
see.
the chat.
Yeah, I'll give you the code because I need to I have to be able to share my screen, but can't do that exactly yet.
No, we only have 14 minutes for Kahoot.
Didn't she just say we can go overtime?
Yeah, I know.
P2000 shall still destroy you all. And also, I made a fire snake. See, fire snake. Fire snake.
Let's see.
Alvin, do you have any ideas on pizzas?
I don't know. I say we just copy we just copy electric P and remove all those electrical currents, and then that's it.
I think actually I have another idea. We can I can just like copy and paste it and then edit it like with drawings. Yeah, I think I can do that.
Yeah, you can draw, but how are we gonna draw on mine? Because we need remote control, you know.
I can share the file to you. I can share the file to you.
How are you gonna share the file to me? Wait a second. Yeah, how are we gonna share the file to me?
Discord.
Okay. Oh yeah, okay.
And I'll just share your screen because we need to still look at the questions. And Boo's
Yeah.
only have 13 minutes left.
No.
Let's see.
Snack.
I don't know if
15, 14, 13, 12, 11, 10, 9, 8, 7 seconds of time. I'm gonna destroy the computer. 4, 3, 2, 1. Oh no, we only have 12 minutes left.
I don't know if they're there.
55, 54, 53, 52.
Okay, so what happened was I got kicked out and I wasn't the host anymore, but then I'm the host, or I guess I'm supposed to be the host again so that I can enable screen sharing, but Cloud Classroom is the host right now, but I don't know if they're active. It says that they're on the call.
So wait. And first of all, why did you enable screen sharing for hosts only? Because if this happened, we can still play Kahoots.
I think it's just like a rule that they might have for the organization.
Maybe it's probably because they don't want people just randomly sharing silly things, like, you know, somebody in the middle of the class sharing dirt memes. No, it's just like it's just something like of a rule so they don't.
What if you read the questions out? And no, that's not good enough. We can do that.
That's not good enough because we don't even know what the answers would be at
and then time would run out.
Time was run out before we even figured out which is which.
Time will figure out after we even time will run out before the teacher reads the question and answer choices and we write them down and don't eat ninjas. The ninja will use their 金箍棒 and cause chaos inside your tummy. I don't care. Just especially with Sun Kong.
How can Sun Kong be a snake? That's not even one of his 72 forms.
Whatever.
Literally, you can Google the 72 forms he has, but he cannot turn into a golden snake that has literal magma coming down from his body. No.
But what if Zhu Bajie had one of them? 36 forms.
Actually, I think he would have less fat.
Well, okay. At this point, I don't know if because if I can't screen share, then I can't really do anything.
How about Discord?
Discord. Yes,
Yeah, Discord.
Discord.
So I think I'll just actually,
Discord.
I mean, we have 9 minutes of class left. I might just finish like class early because, yeah, I don't know why they're not responding. It just seems that they're not active, but if I can't screen share, then I literally cannot do anything. So I think
Oh, I just thought of a great name.
I think I'm just gonna go ahead and end class for today. But I will we can definitely play this Kahoot next time. And yeah, so I'll just leave
We're
you
playing
guys.
2 Kahoots tomorrow.
Yes.
I mean next week.
Yes. So okay, so I'll go ahead and end the meeting, but we will definitely play. I will guarantee that we'll play Kahoot next time for sure. I'm sorry that this happened, but like they're just not responding, and it's been like 5 minutes, so yeah, I don't know if they're going to respond, and we have 8 minutes left, so yeah, I'll just go ahead and end the meeting. But yeah, all right, so bye guys.
Bye.
Have a good night or good morning or good afternoon wherever you are.
Bye.
Bye.
Bye. Bye.
Bye.